Okay, so tonight I thought first I'd open it up to questions about the assignments. We got one that's due tomorrow, right? You got the individual assignment due tomorrow, and then there's a group assignment due next week, right? And I apologize for the confusion about the due dates. So let me just bring this over here. This is our announcements. So as a reminder, the individual assignment number 2 is due tomorrow by the end of the day, Eastern Time. And collaborative assignment 1 is due by the end of the day, not this Saturday, but next Saturday, September 27th. So I know there are 2 groups. Each has 4 people. So if you haven't gotten started yet, that's okay, but you probably want to get started pretty quickly. And we'll work through a data set tonight just a little bit, if nothing else, to give you some ideas of what you might try to do. We're not going to do that actual assignment, of course, that's for you guys. But you know, to give you an idea of some of the things you might think about doing, we'll work through another data set tonight. Are there any questions before we begin?
Yes, and the question is exactly on that group or collaborative project, that what is the expectation from each member? We met yesterday and we talked among ourselves within our group, and I think we need a little bit clarity on that how we will move forward.
Okay, so you met online? So you guys had a conference? Yeah. Okay.
That's correct.
I guess, you know, at this level we sort of start to trust that you guys are going to work together and that everybody will contribute. So what we really do is we evaluate the group on the quality of that final project that you turn in. So I won't ask for a breakdown of who did what. I just want to look at that final assignment, and that'll be what gets the grade. The exception to that, if you have trouble with your groups, I'm hoping that at this level, grad students, you can work in a group and we don't have to worry about managing the groups. But if necessary, contact me and I'll resolve any issues. In particular, if there's anybody that's just not showing up at all, let me know right away, and I'll so if anybody hasn't actually started participating by the end of day tomorrow, let me know, and I'll reach out and find out why not. So we're expecting everybody to carry their own weight. If you're carrying on asynchronous discussions, use your group discussion forum, and I can see that. So if if somebody says, Aaron's not pulling his weight, and I go in and I see that Aaron is posting all sorts of things and nobody else really is, then I'm going to wonder why they're saying Aaron's not pulling his weight. Maybe there's a communication mismatch, somebody's using the wrong location, I don't know. So it doesn't really answer your question very specifically because I don't want to, but I
believe we got enough clarity. That's where
okay.
we were confused that how we will move forward and how each person will have the assignment and those kind of things. I believe we got an answer on that.
Okay, good. Yeah, and I would suggest, we're going to have several of these throughout the term, probably 5 or 6 maybe. Any that the syllabus I think says 7, but if we don't get to all 7, you just get credit for whatever we don't get to. But, if you want to identify within your group a team leader and then rotate that from each project, right? So maybe you do it this time and then somebody else does it the next one. That'd be great. If you guys settle into roles that you're all comfortable with and you want to stay in those roles, that's fine too. I'm not going to manage that. Part of this is just to give you guys a chance to learn to solve some interesting problems collaboratively.
Thank you.
So, but of course, any issues, let me know. Any other questions? Okay, a couple of bookkeeping details. I'll just let you know. After the assignment is turned in for Module 2, on Saturday, I got to update the text on Module 3, but on Saturday, Module 3 will go live, and it's similar to the first 2, except each of the sections of lessons has suggested problems, and all of them now have answers for Module 3. So I know in modules 1 and 2, not all of the suggested exercises actually had answers given, but in module 3 they all do. And then I'm starting to put the videos in there as well. So from module 3 forward, things should be much more complete, and that'll go live on Saturday. In the meantime, if you have any questions on modules 1 and 2 that you wanted to go over, we can do that tonight, or we can do that one-on-one or during office hours. The one thing I'll say is I will not have office hours next Tuesday, and the reason for that is that I will be flying back from Kansas, so I won't be able to. But what I will do is I'll check to see the availability for Wednesday, and maybe we can do something on Wednesday. And in the meantime, if you need help, I'm available one-on-one by appointment all the time, so don't hesitate to reach out. We can set up some time, but just next Tuesday night won't work. So let me know if you need additional time, and we'll set it up. Okay, let's see who all's here just for my own clarity. Let's see, so we've got Vincent, we got Sherrod, Partho, James, Aaron, and waiting for name. So, okay, and this session is being recorded, so I'll post it tonight after class. The last session didn't work, but there wasn't any content, and I now have it working. So fingers crossed, I'll post this probably about 9 o'clock. So what I'd like to do first, I'd like to do two things tonight. The first will be dig into a data set just a little bit together. It's not the one that you're going to use for your project, but it's just another data set with another question being asked. So let me bring up our studio here, and let me read in the data set. And so I have some code written off screen here that I'm just going to use so it's quicker. So if you're wondering how it's magically appearing, that's why. So this is a data set, and I'll describe the question to you here in just a second. But let me open this up. So this is based on a situation from the 1970s where there was a trial of a guy down in Hidalgo County, Texas, and he was being tried for armed robbery, and he was convicted. And he appealed his conviction on the basis of jury discrimination, which is to say he was of Mexican ancestry, and the jury that he had only had 7 out of 12 people of Mexican ancestry. And, for most of us, that's probably, why would you say there's jury discrimination? But the reason for that is that the county he was in was 79, almost 80% of Mexican ancestry. And so 7 out of 12 is well less than 80%. And so he felt that his jury was not fair. And so this is a data set for 70 juries. This is fictional data. I generated this based on the numbers. But this is a data set for 70 juries during that time period. And the only information it gives us is whether the juror is of Mexican or non-Mexican ancestry. And so the question we would be asking is, was 7 out of 12 unreasonable? And the broader question is, do we think there's jury discrimination going on here? And so this is a data set that we might be able to use to answer that question. So I'm just going to open it up to you guys. What are your first thoughts? What are the first things you might want to do?
Maybe you want to look at the percentage of rows and majority Mexican, majority non-Mexican to get a quick idea on how majority Mexican.
So you want to say if a row has more than 6 of Mexican ancestry, then it's a yes, and otherwise no? Is that?
Yes, I mean, I guess it's all going to depend on what your definition of fairness is with regards to how many jurors are made up.
Right. Okay. So
the thing you said was 80%. So figure out the percentage of rows that are more than 80% Mexican or less than 80% Mexican.
Okay. I'm going to do some. I confess I used this data set in my other class just to show them data manipulation. So I'm going to run those quickly just to put it in a different format. I'd be happy to share this code if anybody wants it. It's nothing special. So let me just run this. And all I'm doing here is creating it so that it's of a single column like this. And so we can now do the kind of thing that you're asking me to do. So let me run these quickly. So that was James, I believe, right? So, okay, so I'm going to create a flag column, and that'll let me do some aggregations here. Okay, so what I've done is I've just created a data frame that tells me, actually I haven't done it yet, now I've done it. I've created a data frame that tells me what the composition of each jury was in terms of Mexican ancestry. And what we can see here is for each jury, 50% would be equivalent to 6 Mexican ancestry jurors. And so this will give us a quick idea of what they look like. We could scroll through this and take a look, and we'll see there are a couple of 8s in here, but I don't see any 9s, 10s, 11s, or 12s. And if the population is 80% Mexican ancestry, we would expect more than that, right? So we can actually table this and get a sense of how many juries have each number. And you can see all of the juries have 8 or fewer jurors of Mexican ancestry. So this should be troubling from the start in terms of answering this question. This should be bothering us at this point just a little bit. And so there are a couple of things we should rule out first. What should we rule out first? I mean, if you're told it's an 80... Oh, go ahead, Sharad.
I was about to say something.
Okay.
Yeah, I guess we need to know if the defendant... It doesn't matter if the defendant is also Mexican. So some of those trials...
He is. I'll just tell you he is. Yep. I believe his name was Rodrigo Partida.
Right. Would it pertain to know for each row whether or not the jury was in a case regarding a Mexican defendant?
That's actually a very interesting question. I hadn't thought about that. I don't have that data. But I think, while that's an interesting question, I think we can avoid that question by saying what we're really after here is whether each jury is representative of the county.
Right. That makes sense.
And so, if the county is 80% Mexican ancestry, then we would expect typical juries to be about 80% Mexican ancestry. But even more basic than that, so you're getting into the questions that are digging deeper into the situation. I'm asking, what should you rule out in terms of the data itself before you even do any analysis? Just a very basic question.
So ancestry number, which is a 1, I think, I don't know.
Are you getting at some way of making sure that the data is clean or doesn't have errors in some way?
That it's reliable, yeah.
Right.
So we have a course in the program called Data Acquisition and Management. We're soon to have a second course on data exploration and outlier analysis, probably next year, both of which would tackle that question, right? Taking a look at the data, asking whether it's reliable, those kinds of things. So we should rule that kind of stuff out. Now, that's not the focus of this course, but so you can assume that this is a clean data set, and you can assume for the project as well that I'm giving you clean data sets. So I just say we should acknowledge that that's a concern and make sure we've addressed it. Okay, so now the question James asked about what about the defendant for each of these trials? That's a good question to ask. There's always talk of different defendants getting different treatment, and so we might ask that kind of question. For instance, if you have a white defendant, are they tending to get more jurors that are white on their jury? These are all interesting questions, but I think, again, our overarching question is going to be, for a typical jury, what do we expect, and is this giving us what we expect? So I'm going to start a Word document that we can use to record some results. In the meantime, what else would you want to see?
guess results don't change over time, or we don't have any correlations like days available, or I mean, maybe like responses. I mean, are more Mexicans declining jury duty, or for some reason?
Okay, so that's a great question to ask, and in fact, I think we should postpone that until we know whether these are typical juries or not. So if
percentage of participation, how is that what we need to check?
okay, yeah, so we could do. We want to know. Let's see if I get this right here for you. Excuse me, I'm using the wrong one. Data 3. So we've got 321 of Mexican ancestry and 519 of non-Mexican ancestry. And so if we wanted a percentage, we can obviously see it's already less than 50%. About 38% are of Mexican ancestry, 61% are of non-Mexican ancestry for overall. So I'm going to add that to our notes here. So 38% of jurors are of Mexican ancestry, 62% non-Mexican. Okay. And again, that gives us a bit of a warning here, right? We're a little worried about that. What else? What else might you ask? So remember, somebody has come to you, perhaps from the legal office for the state that's about to defend against the appeal, and they're saying, do we have a defense here? Is what we're getting reasonable, or is there a problem? So what kinds of
Mike,
things?
are we limited to the data set, or can we ask open-ended questions here? I mean, is it within the context of the data, or can we ask questions like what the requirement for the jury pool, what are the ages, or what's the age distribution in the county? Maybe they are not mostly like young children. How are they being counted?
Okay, so those are good questions. I think what I would answer there, keep in mind I'm making up some of this just as we go, but probably what we would say is the 80% figure is for eligible jurors. Right, we would look for the county and say, how many are there that are eligible for jury duty, and of those, how many have Mexican ancestry? So those are great things to clarify. It's not entirely clear that the 80% comes from the eligible jurors, but let's say that we verify that it does.
And there's no statistics on, like, I don't know, based on income and how likely you are to accept a jury summons or not?
Well,
So.
no, we don't have that. Again, those might be interesting questions, but
He claims eligibility, right? So I think that's how the assumption is these are all would be considered and they would accept it. Is that how you're framing the question, Mike?
well, so maybe, yeah. So, I mean, there are people who don't show up for jury duty, but they risk pretty serious penalties when they don't. I just had jury duty a few weeks ago, in fact, and I was very lucky to have married the daughter of a federal attorney, and that always gets me out. But
Actually, it's funny because I was called for jury duty and I'm not even a citizen. So.
Wow. Okay. Well, that should probably get you out too, right?
Yeah. Actually, it took me a few tries to get out of it.
Wow. I always have a fallback that I teach critical thinking, so you don't want me on the jury, right? So both lawyers will send me packing. But
all right. So another question is whether the lawyers themselves, their ancestry, if they're filtering out Mexicans or non-Mexicans. that's not included in the data set too.
Okay, right. We don't know whether the lawyers are choosing to exempt jurors of particular ancestry. I know not so much with Mexican ancestry, at least not a long time ago, but with African American juries in the South, this is a big problem, right?
So I guess one question you could ask is what's the probability of getting these results, assuming that this was random?
I'm writing that down.
Woohoo!
All right, that is a great question to ask. And that's what this course is about, right, is measuring statistically what's the likelihood of a particular outcome. There are a number of ways we can now go about answering this question, actually. And then this is going to lead me into a little bit more of a lecture-y kind of approach here for a minute. But in the next module, so I'm going to start a new section here. You're going to start learning about probability distributions. And I'm going to make this a little larger here in just a second. So. Okay, so we're going to start learning about probability distributions in the next module. And so you may or may not want to make use of that for your project. You don't have to actually do so, at least in terms of the specific named distributions. But for a probability distribution, again, it's fairly simple stuff. There's a list of possible outcomes, each of which has an assigned probability. So I'm just going to make a note of that. And when we take the entire list, those probabilities all have to add up to 1. And so what we can do from the raw data that we have here is we can estimate the probabilities of different outcomes based on this data. So if we wanted to say, what's the probability of getting 0 jurors of Mexican ancestry, 1 juror of Mexican ancestry, and so on, we can actually approximate that now from this data. Right? And there they are. There are your probabilities of each of the outcomes based on this data. So based on this data, what's the probability of getting a jury with 12 Mexican ancestry jurors? We would say 0, right? It never happens. So this class is we're going to start looking at more and more complicated ways of doing things like this as we go. If you've taken a good intro stats class, you might already be thinking about t-tests. You might already be thinking about things like standard deviation and expected values. And those are the kinds of things that we want to use here. So let me just make a note. Each distribution has those things. And we often call expected value mean, right? So we'll call it either. And you should have started reading about how to calculate these things, right? So for this distribution, I'm just going to, oops, I don't want to do that. I'm going to paste this set of numbers in. And we can now take our let me do a quick data tweak here. Okay, let me use those. It's a little smaller list. So we can create a table for each of the possible outcomes and its probability. Oops. So this is our probability distribution from the data. And we'll learn, as I said, we'll learn fancier ways to estimate these things as we go, because we probably won't want to make a claim that these things have 0 probability, but just that they're pretty unlikely. And we can get a graphical view of this from RStudio as well. So let me do that and just throw it in our notes here. So there's a visual. Okay. And I'll throw that in here as well. Just so we have reference to it. And so this is now a probability distribution, and we can use this to answer questions about what's the likelihood of getting a particular jury makeup. This differs significantly from what we would expect, right? We would expect this to be centered around 80%, and it's clearly not, right? It's not anywhere near. 80% of the data would be about 9.3 Mexican ancestry jurors. And yeah, James, I'll share a copy of this, the code and the Word file. And so this is clearly different. Something's going on here. And we could, if we were the legal team, we would start digging into what might be going on. And my guess is one of two things is going on. This is my own personal guess, and it's purely a guess. Remember, the statistician is meant to offer the numerical analysis and then might offer some tentative conclusions to explore, but that's not really our job. So this is the tentative conclusions to explore. One of two things. I don't know about Texas, but in Michigan, a lot of the Hispanic population is migrant workers, and you can't get called to jury duty if you don't have a mailbox. So there's one possibility. Another possibility is that there is actual discrimination going on. So those would be the two that I would suggest first worth exploring. You guys might come up with others. There are no wrong answers. Well, no, I'm not going to say that. There are always wrong answers, but there are plenty of possible answers, right? But again, your job is really more to dig in and suggest and say what the numbers are telling you. What is the data suggesting is the case? And then let them figure out the explanation for that. If you offer suggestions for possible explanations, that's fine, but that's typically not our job. Although in the data science world more broadly it might be. So this is a distribution that you might use to try and answer these kinds of questions. So you've got a formula for the standard deviation, you've got a formula for the mean that you can do by hand. Of course, that's painful. Why would we ever do such a thing by hand? So what I'm going to do here is I'm going to take my counts, turn it into a vector, and then if we take a look at x quickly, it's just a vector of those counts. Actually, no, I'm going to do it a different way. I take it back. So we've got a count column here. If we want to get the mean and standard deviation, we can get that, right? Let's see, jury composition. So the average is 4.6. The standard deviation is about 1.6. And so typically we say we expect results that are within about 2 standard deviations. So that means we would typically, based on this, expect juries to be anywhere from about 1 to 7 or 8 jurors of Mexican ancestry, nowhere near the 80% that the population is. So something is going on here. Even just from this basic, simple analysis, something weird is going on. Now, what we've done here is not terribly rigorous, and so this is really just first exploration steps. What we really want to do is reverse the process a little bit. And so this is going to lead me into talking about probability distributions for particular types of problems. So we're going to start talking about the named distributions now. And there are two that we're going to talk about tonight. Excuse me. two that we'll talk about tonight that might apply to this situation that we have with these juries. So the first one we'll talk about is the binomial distribution. And what I want to do is focus more on how do we figure out when a distribution is appropriate for a given scenario. So the binomial distribution is typically appropriate when you're modeling something that has a fixed number of trials. So that'll be our first assumption, a fixed number of trials. And don't confuse that with legal trials, right? Just whatever the experiment is that you're conducting, we just say it has a fixed number of trials. So for instance, if you're going to flip a coin 10 times and record the number of heads that you get, that's a fixed number of trials, right? You're flipping the coin 10 times. If you're going to, if you're going to do something where you roll a die until you get a 6, that is not a fixed number of trials because you're going to roll it some variable number of times until a 6 comes up. So that would not be binomial. So what you'll want to do is for each of the distributions we study, you're going to want to learn what the assumptions are that are behind that distribution so that you can figure out whether a particular scenario matches those assumptions. So for the binomial distribution, you have a fixed number of trials. The probability of success on any given trial is always the same. So for a coin, if you flip the coin 10 times, we have to decide what success is. So let's say heads is success. The probability of getting that success is always the same for the coin, right? I don't think I've ever seen a coin where if you flip it, it changes the probability for the next time. And in fact, if you go to Las Vegas, you can often exploit that. The easiest way, not that I advocate this, but the easiest way to make money in Las Vegas is side bets with people who are watching. So if you're standing near a roulette wheel and it's come up red 10 times in a row, you can find somebody who will bet you that it'll come out black next time. It's due black, right? That's what you'll hear. And so you can find people who make irrational claims and you can actually offer them bets. And you can actually make a decent small amount of money doing that. I'm aware of at least 3 or 4 people who make a living doing nothing but that. It strikes me as kind of sad. But the people playing the games are either there just purely to have fun or they generally know kind of how it works. But the people watching are often a lot less clued into the actual probabilities. So it's a statistician's dream to stand there and just watch people's behavior, at least for me. The other thing here I left off is we should have a clearly identified success and failure. So again, we could say for a coin flip, heads is success, tails is failure. That's arbitrary though, because you could have, if the trials are individual people and the question is whether they contracted disease or not, we might set it up where success is yes, they contracted the disease. But I'm not sure the person would consider that a success. So success and failure is arbitrary. It's just we need to identify which one is the success so that we can use the correct formulas in the correct way. So there's a fixed number of trials. There's a clearly identified success or failure. And the probability of a success is always the same from one time to the next. And the most important assumption is each trial is independent of the others. This is what makes up a binomial distribution. And so when you're looking at a scenario and you're trying to decide whether it's binomial, these are the 4 things you have to address. You have to ask whether there's a fixed number of trials, whether there's a clear success, whether the success is got the same probability every time, and whether each trial is independent of the others. If the answer to those 4 questions is yes, then you can use the binomial distribution tools. So let's talk just a little bit about what those tools look like. So the first tool is what we'll call the expected value, or the mean. And I'm going to say the probability of success is P. That's the standard. And so and the fixed number of trials is n. And those are the only two parameters for the binomial distribution. You need to know how many trials, and you need to know what the probability of success is. If you know those things, then we've got some equations we can use. So your expected number of successes, which will be x, is going to just be equal to the number of trials times the probability of success. And if you think about that for a minute, if you flip a fair coin 10 times, 50-50 chance of getting heads, you'd expect on average to get 5 heads, right? So 10 times 0.5 equals 5. All right, so this is the expected value. The standard deviation, and we're going to learn the theory behind all this. Actually, I'll put the symbols in the equation. We're going to learn the theory behind all of this as we go, but to give you a sense of how these work, the standard deviation, which we usually call sigma, is going to be equal to, for the binomial distribution, n times p times 1 minus p. And I'll just tell you, in many books, they use q for 1 minus p. So it's the same as saying npq. I prefer 1 minus p so that you know that it's, that they're linked, right? P and q are connected in that way that they add up to 1. Because the probability of success plus the probability of failure, well, that's all your options. So that has to add up to 1. So p times 1 minus p is the same as p times q. So your standard deviation is the square root of that. We'll learn how to derive that in a little bit. But this lets us answer typical questions. So let me make a note of that. So for our jury case, let me ask you this. For our jury case, let's consider an individual jury, 12 jurors, right? So does that fit with the binomial distribution? Imagine you're the one picking the 12 jurors from the county's population. Does this seem like a binomial experiment to you? And I'll scroll up so you can see the assumptions. You're picking a jury of 12. So I'll go around the room here. Brian, what do you think? Do we have a fixed number of trials? Yes, we do. Okay, so Brian says yes, we do. And what is that number? Okay, for our jury case, n equals 12. So who's next? James, I've already heard from you tonight. Let me see who else we have here. Vincent. Do we have a clearly identified success or failure?
Yes.
Okay, what is
Whether
success?
they're either mastery or minus. So you want to know if the jury is a majority of Mexicans, or it reflects the population.
Okay, so for each juror that we pick, what would you call success and what would you call failure?
So in that case, I'm not sure. I guess success could be if they're Mexican ancestry.
Okay. So then failure would be non-Mexican ancestry. And you could have done it the other way around and you would have been correct. So we could have said success is non-Mexican ancestry and failure is Mexican ancestry. It's arbitrary which one you call success and which one you call failure. All it does is change the scale of the answers. All right, so how about Partha? What do you think? Is the probability of success on each trial the same? And I'll just tell you the population of the county was about 180,000 people.
So it depends on the population we have, right?
Right.
The juror population. So can I see that data?
Well, so what you need to know for this question, you don't actually need to see the data. What you need to know is that 80% of the population is of Mexican ancestry, and there are 180,000 people that are eligible citizens for jury duty. But let me simplify the question. Let's imagine that there are only 10 people eligible and you're picking one. Or no, excuse me. There are 10 people eligible and you're picking 2. And let's say of the 10 people that are eligible, 8 of them have Mexican ancestry. And so you pick the first person and you write down whether they have Mexican ancestry or not. When you pick the second person, is the probability the same or has it changed?
It has changed because now instead of 1 by 10, it is 1 by 9 because one already has picked up.
Right. And you would need to know what the ancestry was of the first person to say what the new probability is, but it has definitely changed, right? If you pick somebody of Mexican ancestry, now there are 7 out of 9 left. If you don't, there are 8 out of 9 left, and so it's a different probability. So this actually violates the third assumption. Right? Those probabilities are not constant. And so we got 2 choices. Here are our 2 choices. There are 180,000 people. Pretend it's constant. Because in the case of 10 people, it changed quite drastically. But if out of 180,000, about 140,000 have Mexican ancestry and you pick one of them, well, now it's 139,999 out of 180,000, or 179,999. The probability is so close to the same that it really doesn't matter. So that's one option we have, and we'll take that option in a minute. But the other option is to use a different distribution. And we'll look at that if we have time tonight. We'll look at that one as well. And it's called the hypergeometric. All right. So hypergeometric is a distribution that's designed exactly for what we're doing, where what you do is you update the probability each time. And so we'll come back to that in just a minute. But for now, let's do the first. So we have n. The other thing we'll say here is each trial is independent of the others. We'll assume that it's true. We don't know for sure, right? We don't know how they're actually picking the juries. But what we're going to do is assume that it's true and see what that leads us to. And then when we do that, we'll see whether our actual results are matching with what we are assuming is true. So, okay, so we've got probability of success is P equals 0.796 is the number that I've got. And so we've got 12 trials and a probability of success of P equals 0.796. So what we can do is use a calculator, or in this case I have a very powerful calculator here. So n times P is 12 times 0.796. So we have an expected value of 9.552. So let me make a note of that. So on average, we would expect 9.5 jurors of Mexican ancestry. So we already know that our 4.58 is way off. The other thing we'll do here is we'll calculate the standard deviation. And again, I'm going to use this formula. I'll provide the formula to you in these notes. But what I'll do is the square root of 12 times 0.796 times 1 minus 0.796. And that gives me 1.396. Oop, didn't want that. Okay, so our standard deviation what did I say? 1.396, I believe. Let me double check that. Yep. Okay. Now, a simple rule is that typical results will be within about 2 standard deviations. And as we go later in the class, what we'll learn is that that's about 95% of the cases. If we did 3 standard deviations, that would be a little over 99% of the cases that would be within that range. So if we look at this, we would say take your expected value plus or minus 2 standard deviations. And that's what we would expect as a typical result. So if we do that arithmetic, let's see, I'm going to just do quickly in my head here. We've got 9.5 minus about 2.8. So that brings us down to about 6.76. So let me write it as an interval here. 6.76, and then 9.5 plus 2.8 takes me up to 12.3 or so. And so for our purposes, a typical range of jurors would be 7 to 12, right? So that's what this is saying. If it's truly a binomial situation, then we would expect between 7 and 12 jurors of Mexican ancestry 95% of the time. Let me just remind you what we get in reality is this. Are the majority of those between 7 and 12 jurors of Mexican ancestry? No.
No.
Not at all. So something is clearly wrong in terms of the situation. Something's not working the way they think it should. Now, let me ask you a more important question for the particular problem, though. He had 7 jurors of Mexican ancestry, and he's appealing on the basis of an unreasonable makeup of his jury. Is 7 unreasonable based on what we just said?
No.
No.
No, it's not. So now you've got an interesting question. Clearly the process is not working the way it should, right? The makeup of the juries typically is less Mexican ancestry than it should be. But in his specific case, it wasn't. And so now the attorneys that are going to be fighting this in court have a decision to make. Which of those is more important? Does it matter more about his individual jury, or does it matter more about the overall process? That's not a question we can answer as statisticians. What we can do is say the typical results are from 7 to 12. And in this case, he fell within that range. But overall, the process is not giving those answers. And we could go back and we could calculate whether the overall result is reasonable. And I think, if I remember off the top of my head, if you figure out how many standard deviations away the actual number is from the expected for all 840 jurors, it's something like 24 standard deviations away from what you expect. And that's not reasonable. So the overall process is clearly flawed in some way, but in his case it's not. And so what do you do with that? I don't know. You hand that report to the people that asked for it and you let them make up their minds. Again, you might offer some tentative conclusions, but that's really not what you're being asked to do. You're being asked to provide these numbers and supporting analysis. They're asking you, is there a problem? You give them the numbers that can answer that question and then let them interpret it. Okay, so Aaron, you say a quick question?
Yeah, so for the binomial distribution, our maximum value, the number of trials, is 12, yet we're getting, what does that mean when you get a standard deviation that puts you over 12? I mean, what if it were, 3?
So what it tells you is that at the upper edge there's nothing unusual. So within 2 standard deviations is one way to say what's typical. So we would say typically you'll fall in the range of 6.76 to 12.34. Well, we know we can't get 12.34. That's why I capped it at 12. And we know we can go down as low as 6.76, which includes 7 but not 6, right? 6 is outside that range. So all we would say is that at the upper end there's nothing unusual. All of the unusual possible outcomes are below 6.76. But if we have a probability of 0.5 for success, you'll have unusual stuff at both ends.
I guess I'm used to normal distributions where there's sort of no end, right? They both go to infinity.
Right. So the binomial distribution is not set up that way. Obviously, it's a discrete distribution with an upper limit. So if the range that you calculate falls above that upper limit, then there's just nothing unusual on the upper end.
Okay.
Or if you get a lower limit of -2, then there's no unusual small number of trials. Sharad?
Oh yeah. I have a question about a question such as will it rain tomorrow, or is my train going to be delayed tomorrow, be considered a binomial distribution?
Well, so it would be a binomial of 1, right? The problem you're going to run into, one trial, the problem you're going to run into is that calculating that probability of success is not easy. There are so many factors that go into it that you could treat it as a binomial, but you won't know the probability of success. Now, Bayesian statistics offers a way to deal with that, where you start out with, well, what do I think the probability of success probably will be? And then you update that based on additional evidence. So you might say, oh, go ahead.
So in terms of the weather, when they tell you there's a 30% chance, or is it likely to rain tomorrow, what kind of model would they be using?
Well, the simplest model that they use for that is, this is very naive, so they do more complicated stuff than this, but the basic way to interpret that, 30% chance of rain tomorrow means under the exact same conditions that they're expecting to occur, it rains 30% of the time. So if they look at the last 5 years, they look for all the days of the same temperature, the same pressure, right, the same humidity, 30% of those days it rains. So they say tomorrow there's a 30% chance of rain. That's the kind of thing they do for weather forecasts. And of course they don't do it by day anymore. Now they do it on a very fine scale, right, by hour or even less than that sometimes. Does that answer your question, Sharad?
Yes, it does, because okay. I was trying to understand if it would qualify, because you could force it to qualify for those 4 criteria. Yeah. But I was trying to do the math, and not very helpful. It's all you would get is like yes or no, which is not. Well, you end up where you start with.
Right. So it's actually not a binomial. That's a Bernoulli trial. And a Bernoulli trial is a binomial of size 1. It's just a single trial. So so I guess it is a binomial, but it's really typically called a Bernoulli trial. The thing you could do with those forecasts is, if you watch the forecast over the next month and you look for all of the days where they say there's a 30% chance of rain, let's say they'd say that 8 times. What you could do is track whether there is actually rain or not that next day, and you could use this approach to calculate what the typical accuracy would be, right? So you'd say 8 trials, probability of success is 30%, calculate the expected value, right? It's going to be 2.4, calculate the standard deviation, and then say, okay, typically we would expect between 0 and 6 days of rain, or whatever it comes out to. And then you say, okay, over those 8 days it rained 5 times. That's typical. They're not off, yep. Right? They're within what we would expect to be normal success rate.
I see.
Does that make sense?
Yeah, it does.
Okay, good.
Thank you.
The hardest part with these things, and there are several distributions. Unfortunately, we're not going to have time to get to all of them, but I do want to just briefly look at the hypergeometric in a minute. But we're going to cover, I think, 5 total in the book. It covers binomial and Poisson, and then it also covers hypergeometric and geometric. And then there's a 5th called the negative binomial distribution. I don't think that one's actually covered in any depth in the book, but those are the most common ones. And half of the work in doing probability modeling is identifying the correct distribution. So there is a correct distribution, for instance, for the data set for your project, but you don't have to use it. You can use the raw tools. You can look at the distribution itself from the sample and calculate the expected values and calculate the standard deviations from the sample and work with those. Or, as we'll learn how to do later, you can identify the correct distribution and then use its theoretical values instead. But let me talk a little bit about the hypergeometric distribution before we go. So the hypergeometric, I'll put this on a new page. Let's list out what goes on for this one. So it is still a fixed number of trials, right? And there is a clear success. Clearly not my typing tonight, though. So clear success and failure. However, trials are not independent. Sampling is done without replacement. So this is the case where once you pick somebody, they're picked, and the rest of the population, you update your probabilities. And so for the hypergeometric distribution, in the interest of saving time, I'm going to find the formulas in a document I have elsewhere and copy them over. So here's, actually here, this isn't bad to see. This is a flow chart, and I'll send this out as well, that walks you through how to identify the distribution. So is the total number of trials fixed? Yes, we're over here. Are the trials independent with identical probability? If the answer is yes, then you've got a binomial. And if the answer is no, then you've got hypergeometric. But if the sample size is really small compared to the population, and our rule for this class was if the sample is less than 1/10 of the total population, you can assume that binomial is okay. So with 180,000 people to pick from, if we're picking a jury of 12, that's 12 is clearly less than 1/10 of 180,000, so we could use the binomial if we wanted to. But in strictly speaking, we would use hypergeometric. And so here are the formulas for hypergeometric. The expected value is the number of trials, n. That's your sample size, so 12 for juries. And then it's R over n, where R is the number of successes in the population, and capital N is the total number of people in the population. So that's very similar to P for the probability, right? 30 people out of 50, or 140,000 out of 180,000. That's your probability P. The standard deviation changes, though. We have N, just like before. We have P, just like before. It's that R over N. And we have 1 minus P in the form of 1 minus R over N. That's identical to binomial. But then we have this correction factor. So for hypergeometric, because we're not sampling with replacement, we have to correct. So we do capital N minus lowercase n, which is total population minus sample size, divided by capital N minus 1. So in our jury case, this is going to be 180,000 minus 12, divided by 180,000 minus 1. That's almost exactly 1, right? This fraction is virtually 1. That's why the standard deviation will come out to be about the same, and that's why we would be okay using binomial instead of hypergeometric. But if we only had 100 people here, this would be significant, and so we would have to use this correction factor. So the book goes into more detail on these different distributions, but this is the idea of trying to answer questions using probability. We want to use the probability distributions in order to approach and model the data and see whether the results we're getting are typical. So we're out of time, unfortunately. We could go on a lot longer. But this is the kind of thing I want you to do with this collaborative project, is try and identify what's the expected value, what's the standard deviation, so what's typical for him, what are the probabilities of each number of sandwich being demanded each day, and then use that information to try and optimize his how many sandwiches of each type he brings each day. So use these different distribution concepts. You won't need to use, I'll just say, I may have led you down the wrong path here. You don't need to use the standard deviation much for this project. You'll need that more for the next one. For this one, really just try and map out what the probability distributions are for the different sandwich counts, and try and use that to answer his question. I'm perfectly happy to be helpful during these as well. It's not go and do it without any help from me. So as you're trying things, either post in the Ask Your Instructor forum or post in, or send me an email, and I'm happy to help. I'm not going to give it away, of course, but guided learning is our goal here. So, all right, let me wrap it up because we're out of time. Any procedural questions before we end?
So, Mike, you said no office hour next week, right? But we can schedule it directly with you?
Yeah, I'm available Monday.
Okay.
The problem with Tuesday is I might be able to be available, but I'm at a conference. I'm at a genomics conference, and I'm presenting during the day Tuesday. So there's a chance I won't be back in my room in time.
What's the probability of that?
Yeah.
Good question.
Well, the frequentist in me says that this event has never occurred before, so we can't answer that. The Bayesian says 50-50. Because it's all subjective. So, yeah, I don't know. And in fact, I would be happy to show up in case I could be, or say you can show up and see if I'm there, but I think it would be better to just do it by appointment. Yeah. And I'll be available Monday night. In fact, most of the day Monday I'm probably available too. I'm flying on Sunday, so I'm not available Sunday night. But and I'm available Wednesday night, all day Thursday, and all day Friday. So just reach out if you have questions, and we'll find a time somewhere.
Okay.
All right.
Okay. Thank you.
And just so you know, I'm going to back off a little bit in terms of the number of assignments. So you'll have a group project due 1 week, and then in the intervening week you'll have an individual assignment, and then another group project the following week. So they'll alternate rather than having 2 at once. So we're trying to get these numbers right. We're trying to figure out what's the right amount of work. I know that it's a lot, so I'm going to back off just a little bit in terms of the number of individual assignments. So each week you'll have 1 assignment due. It'll either be group or individual, but not both. Okay?
Wonderful.
Okay.
Thank you.
Anybody who wants more work, I'm happy to give extra problems, but...
we have 609 for that.
Right.
Yeah.
Right, that's what I'm told. So, let me know. And if I ever give a deadline that's identical to a 609 deadline, and I'm willing to, there are only 8 of you, I'm willing to push that back a little bit if necessary. Just, you got to let me know. So, I'm trying not to have everything due on the same day in every class. That's my goal. So, and I'll try and be more consistent with deadlines on documents. It really is a monster. We have to change it in like 5 places. So, if it happens again, just assume it's whatever the latest one is that's published. Then we'll be good. Okay, I'm going to sign off. Thanks for coming, and good luck with all your work.
Thank you.
Thank you.
You're welcome.
Good night.
Thank you.
Bye.
Good night.